Obtain the mesh file and also the full training movie by purchasing this product.
In this project, we will simulate a Heller dry cooling tower. A dry cooling tower is used as a means of indirect heat transfer between the working fluid and the coolant. In a thermal plant, the working fluid exits the condenser and then is pumped into a ring of heat exchanger. These heat exchangers are air-cooled, which means that they are cooled by natural air suction caused by a temperature difference between the inside and the outside of the cooling tower. The more the temperature difference exists between outside air and working fluid, the stronger the temperature driving force. In this project, the airflow inside a dry Heller is simulated. The airflow inside the Heller construction is heated, and due to the temperature changes and based on the ideal gas law, the airflow will lose its density and therefore move upward and outside the Heller construction. The geometry of the present project includes a cooling tower, heat exchanger, flow domain, and an air inlet. The geometry is designed in Gambit software. The geometry is also meshed inside Gambit software. The mesh type used for this geometry is unstructured, and the total element number is equal to 1,343,988. A new window will appear showing you the DOM and extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh is designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now, there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure-based since we are derivating compressible flows. As for the velocity formulation, we have set the absolute format, and as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. Also, as was previously mentioned about the gravity, you can see here that we have enabled the gravity, and the value of gravity is defined to be equal to minus 9.81 in z direction in order to capture the effect of buoyancy forces and changes in density due to the temperature changes. After double-clicking on the viscose button, a new window will appear. In the appeared window, you will see that we have chosen two equations, standard K epsilon, to solve for our fluid flow. The standard K epsilon model is one of the most renowned models for solving the turbulent fluid flows, and actually two equation K epsilon model allows the determination of both a turbulent length scale and time scale by solving two separate transport equations. Also, under the thermal tab, the thermal condition of coupled is defined for this wall, and by defining coupled, we mean that this wall is in contact with fluid on its both sides. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now, in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. After double-clicking on the Run Calculations button in the appeared section under the Parameters part, by just defining the number of iterations and then clicking on Calculate button, the software will start the simulation process. Now in this part, we have extracted 3D and 2D contours by the means of CFD Post software. Now in this 3D contour, which is related to the velocity, you can easily see the airflow exiting our Heller construction with a higher velocity comparing to the airflow in the ambient region. Now in this contour, you can easily see the temperature distribution in the middle section of our computational dummy. As you can easily see, the airflow exiting the Heller construction has higher temperature comparing to the ambient temperature. As you can see in this contour, the airflow streamlines exit the Heller construction with higher velocity and higher temperature. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.